How's it going? All right, so today we're going to discuss graphs of rational functions, and just pretty much rational functions in general. Sort of will be an introduction to rational functions, and then I would like to talk about one of the main things that we can explore with rational functions, and that's the concept of discontinuity. So if there's any sort of x value in the domain that is not permitted, then we can talk about what happens there. And so discontinuity usually occurs around undefined elements. And then the other thing we would talk about too is end behavior, which is what's happening to our function as x goes toward infinity. So let's get started. All right, so the definition of a rational function is it's in essence just the ratio of two polynomials. So a polynomial is something that hopefully you know what that is, and just know that a rational function is strictly, its definition is it has to be the ratio, a fraction of two polynomials. And the one thing, once you have a fraction, that you need to consider is when is my denominator 0? Because if the denominator 0 is, then we have some problems. So we have to resolve those. All right, so let's practice real quickly. Finding the domain for these rational functions. Now they're all called R, so I'm just going to write domain with a capital D, or I'll just write a capital D next to each one. Okay, so the only thing that could possibly make this function for part A here undefined is the denominator. So we'll take a look at that and say, hey, when is the denominator equal to 0? So we say x plus 5 equals 0. That means x equals -5. So when x is -5, the denominator is 0. And when the denominator is 0, we are undefined. So the domain is going to be all real numbers such that x cannot be -5. Now, another way that we like to write the domain is in something called interval notation. So if you think of all real numbers, normally you'd go -infinity to infinity like that, but we have a break in our infinity of real numbers. So we can go from -infinity up to -5, but not inclusive, union -5 to infinity. Struggling here. Let's try that one more time. Whee! All right, so there we go. And let's shrink that down, move it over here. All right, so you could format your domain either way. Personally, when you're dealing with rational functions, I particularly like this one because it's a nice way to list all of the things that are undefined. As opposed to this one, you have to kind of like look for the breaks, the beginnings and the ends of the intervals. So I'm going to stick with what you would call set builder notation. That's that first one that I just highlighted. Next. Okay, so when is the denominator of this equal to 0? X minus 4, or x squared minus 4 equals 0. X squared equals 4. X equals plus or minus 2, because when we take the square root of both sides, plus or minus. All right, so if I were to plug in positive or -2 over here, I'm going to get undefined elements. So I'd say my domain is all real numbers such that x cannot be -2 and it cannot be 2. Some people are thinking like, hey, why aren't you saying just plus or minus 2? When you're dealing with rational functions, it's nice to itemize each undefined element because each one might mean a different thing when we go to graph it. So believe me on that. Next one. All right, we have x squared plus 1 equals 0. That's our denominator. Now, some of you might look at this and be like, that's never going to be equal to 0. You just might have really just keen number sense. If not, you know what? It's fine. Just try to solve it. So it's going to go x squared is equal to -1. Again, you're like, what number times itself is equal to -1? Really, nothing really does that. That's real anyway. And then you go to take the square root of both sides and you quickly find out, oh, x is equal to plus or minus the square root of -1. And we only want real results here. Some of you might be like, but it's plus or minus I. True, but we're not looking for I right now. We're just looking for real numbers in our domain. So actually the domain for this is just all real numbers, because there does not exist any sort of number that I could plug in here that would make this denominator equal to 0. All right, so the domain for that's all reals. And then lastly, I want you to just pause the video and do this last one. Just try it on your own. Go for it. Welcome back. All right, so let's just take that denominator, set it equal to 0. We know x cannot be 1, right? Because when x is equal to 1, everything's undefined. So I'm going to say, here, you know what? I've been saying this the whole time. So we know that if x is equal to 1, it's undefined. So I'm going to state the domain. X is all real numbers such that x cannot be 1, right? Some of you might be thinking, but wait, that numerator factors into this, right? And then you can simplify it. So now we have x plus 1. True. And now nothing is undefined. This would be the equation of a line. That's something that we'll look at later, whether it's with me or with your own teacher. Okay. So that would be the domain. So the moral to this story is that if you have a rational function, the most important thing is that you state the domain before you do anything else. That includes simplifying, because it is possible that when you state the domain, if you don't state the domain first and then you go ahead and simplify the rational function, things that were undefined are going to become defined. Like if you look here, I'm allowed to plug in 1 to the simplified, right? But the original, I was not allowed to plug that in. You have to respect the original. So we always state the domain first. So pretty much across the board. All right, moving on. So this is a little activity, and this is pretty much the star of the show today. So we're given this function, 3x squared minus 2x minus 5 divided by x squared minus 1. So we're going to go through stating the domain. I would like to simplify the function because, as the word simplify implies, it's actually a little bit easier to graph the simplified version of the function, but it's really important that we state that domain first. All right, so we've got that taken care of. Well, we will. And then I would like to graph them. I'd like to graph the function. Let's graph both of them, actually, the original and the simplified, just to prove the point that they both look identical. We're going to look at the table to just to explore what's happening around those domain restrictions. And then lastly, we could also use the table and the graph to look at the end behavior and see what that means. And when we're describing or exploring these undefined elements, we are going to use limits. I'm just going to use limits. I'm not going to make a whole lesson out of them. If you are really interested in limits, please tune in another time and look for a video that's related to limits. I don't have one posted yet. Okay, so here we go. So let's look at what we have. Let's state the domain before we do any sort of simplifying if possible. So take that denominator, x squared minus 1 equals 0. So if you go to solve this, I'm just going to solve it the way you normally would. X squared is equal to 1. X is equal to plus or minus 1. So when I go to state my domain, I'm going to say all real numbers such that x cannot equal negative 1 and 1. All right. Notice how I showed my work there? Teachers are very appreciative when you show how you arrived at certain solutions. So I'm going to just shrink this down, maybe put it over here. So you just kind of know where that came from. Now, let's focus on simplifying this function. This is equal to, I'm going to factor the numerator. We're going to factor the denominator. X plus 1, x minus 1. Some of you remember the difference of two squares, right? Well, there you go. And the denominator. Numerator is a little bit trickier, but not too tricky because 3 is prime and 5 is prime. So we really only have a couple options. So let's do some trial and error here. So we know that we need a 2-term in the middle there. I'm going to go ahead and say that most likely this is a 5 here and a 1 there, because I know 5 and 3, when I add them or subtract them, I can get negative 2. So it's looking like this needs to be negative, and this needs to be positive, because now when we FOIL this back out, these two are 3x squared, these two are positive 3x, these two make negative 5x, and then minus 5. So these two together give me that, and we're in business. Notice how I checked my work. It's important. I'm not just doing that because I'm making this video. I'm going to get rid of my work checking so we can now look at what we have. All right, the numerator and the denominator are both in factored form. If we notice that we have some common factors here and there. So I'm going to divide those out. It's gone and gone. So because anything divided by itself is equal to 1. So that leaves us with 3x minus 5 over x minus 1. We can actually work with that function now. So I'm going to come down here and say the simplified function is f of x equals 3x minus 5 over x minus 1. But keep in mind that we are dealing with this domain over here. That's going to be our domain. I have to stick to that domain. So we're going to see what's happening to the function around those values, mainly. Okay, so they'd like us now to input both of these functions into our calculator, which I'm going to do right now. Actually, I've already done that. So most of us use the TI-84 graphing calculator. Have to be honest, it's not my favorite calculator. If you're one of my students, you've heard me complain about this calculator. I can't believe that we're still using this. I'd much prefer using a program like Desmos. But anyway, this is pretty much what's on many standardized tests, especially if it's a computer test. They expect that you're going to use this calculator. So I'll use this. All right, so I've entered the original function and look at the graph. That's what it looks like. Okay, so now what we're going to do is we're going to enter the simplified function that I have right here. So it's just 3x minus 5 over x minus 1. So when I arrow down to this next function here, little pro tip, if I believe it's you press the alpha key and then y equals, and you have you get this nice little menu of fractions that you can plug in. So choose option 1 that enables us to have just a fraction bar. You don't have to worry about using parentheses this way. And then we're going to go 3x minus 5 divided by x minus 1. If we hit enter on that, take a look at the graph. Graphed right on top of the other one. Fantastic. Now, if we look at, if we just take a look at this graph, you can see that at positive 1, which is consistent with our domain here, right? At positive 1, we have something that appears to be undefined, right? And if you have experience, you know that there's a vertical asymptote there. At negative 1, though, right here in this spot, the graph seems perfectly continuous. Doesn't seem like there's anything wrong at all in both of them, in both the red and the blue graph. So I believe I can turn off the red one right now. Just let's see if that worked. Yeah, it looks pretty good. So that's just the original, the one that's not simplified. Again, you don't really see anything missing there. There's no asymptote there clearly. So yeah, I would like to take a moment now and talk about these undefined elements on this graph. All right, so one tool that we have in mathematics for exploring the undefined is something called a limit. So let's focus on negative 1 now. We think, we see that it looks like it's there. So, but I'm technically, when you look at this original function, I am not allowed to plug in negative 1. Right? I'm just not allowed to plug it in. So some people accept that. They're like, yeah, it makes sense. It's equal to 0. But you also want to be curious, and you want to not accept everything just based on faith. You want reasons. You don't want to know why. Like, I'm not allowed to plug in negative 1, so maybe I should try to plug in something that's near it and see what happens. And that's what a limit is. It says, hey, you know what? How bratty can you be? Like, how close can you get to negative 1? without plugging in -1 on this graph? And will that give us a sense for what's happening there? So let's do it. So the way you would write this is, since we're looking at -1, we're going to say, all right, our function is f of x. So I'm going to say, what's the limit? So we're going to state, okay, x is not allowed to equal -1. So that means, and we're going to say, why not? So the tool that we're going to use is the limit. We're going to say, what's the limit of our function f of x as x approaches -1? Now, when you ask that question, when as x approaches some constant like -1, in order to know what exactly is happening there, we must approach -1 from both sides. So there's a notation for that. So in order to get this limit, if there truly is a limit, if there's a value that exists there, then it's going to be the same thing when I approach from both sides. So what I'm going to do then is I'm going to say the same thing. I'm going to say, what's the limit as x approaches, we'll do that part. What's the limit of f of x as x approaches -1? Right there, and that means, you know what, I'll just put that in red. And then I'll just I'll annotate on this one, from the left. So what is that limit? I'm going to come over here, and here's the graph. Now what I mean by that is, as x is approaching -1, -1 is right here, okay? So approaching -1 from the left side means we're going to look at x values like -2, -3, -4, -5. So you plug in like -5, -4, -3, -2, -1. But -1 you're not allowed to, but the approach from the left side is just plugging in those values. Now, of course, these are important, but what's most important is what you'd call like a neighborhood of values that are around -1. So I'm more interested in values like -1.003 or something like that. And I want to know, what is y approaching as x is approaching -1. So it looks like there's something there, actually. The best way to get more information on that is to look at the table that's produced by the calculator. So now one thing that I did not put into the video is this table of values, and how to find that. So let's real quickly just take a moment and just to discuss how to plug that into the calculator. So what you do is go second and hit window that says table set, right? And we want to know what's happening at -1. So we're gonna hit enter on that. That's cool. Starting the table at -1 and say, all right, I want to see what is happening as I plug in x values to y, but starting at -1. And I want to count by 0.01. Actually, let's go 0.1 on this one. 0.01 is fine. We're going to get really, really close. Yeah. All right, let's do that. So I'm going to hit enter on that. That's the change delta table. Leave everything else on auto. Second table. All right. Now we started at -1, but let's back up a little bit. Let's kind of center up that -1 so we can see both approaches. So that's how you get the table on your calculator. This blue graph right here, that's the unsimplified, and the red one is the simplified version. Notice how at -1 on the simplified, we have an answer of 4, that there's no error. Whereas unsimplified, the -1 is still undefined, so you get an error. So it's interesting to note that when it's simplified, it does become defined. All right, so let's switch back to the iPad. So on the iPad, looking at the same thing gives me the ability to talk about that approach. So the left approach, as x is approaching -1, that's happening right here. So as x approaches -1 from the left side, left approach. So you see y, so x is approaching -1 from the left side, okay? That's the equivalent of what's happening here, okay? But if you look, we're really approaching in this interval right here. So I'm not plugging in -1, we're just getting close to -1. And you're getting numbers like 3.97, 3.98, 3.98, or really 3.99, 3.99. So when you're approaching the left side, you're getting these values that are very consistent. They're almost like the same thing. And ultimately, you see in this graph right here, in the simplified version, it is in fact approaching 4. So that's the left approach. And I think you would imagine that this portion right here, that's what's happening as x is approaching -1 from the right side, right? So let's go back over to our limit and talk about the right approach too. So the left approach we just discussed is equal to 4, all right? And then we're going to say, what's the limit as x approaches -1? With that plus side, that means right side approach. So what is y approaching as x approaches -1 from the right side? So we're going to look back over at our table again. So as x is approaching -1 from the right, it's going this way. Y is 4.02, 0.02, 0.01, 0.01, 0.005, which would still round to 0.01, but it's getting closer and closer to, not sure, right? But if you look at both sides of this, if you were to try to average 3.995 and 4.005 together, what's in between there? Clearly, it's 4, right? So there should be a 4 there, but in the simplified version, it's there. The graph is continuous, there's no problem there. In the unsimplified version, you have an error. So what does that mean on the graph, right? Because it's not a vertical asymptote. We know what a vertical asymptote looks like. Definitely not a vertical asymptote. What that means is that you actually have something called a hole. So the way you would draw that is on the graph, you'd say, you know what, I have to remove that coordinate that's in that spot. So I'm gonna draw an actual circle. And that's actually called, let me try that one more time. That's called removable discontinuity. That means that we're just removing that point because it's just, the graph is not continuous there. It's like on a number line where you have all your values and you just put an open circle there or for a non-included value. So I'm not allowed to plug in -1. So the point -1 comma 4 does not exist on my graph. Right? It does exist in the simplified, but we were not asked to graph the simplified. We're asked to graph the unsimplified version. So what am I getting at? If the limit as x approaches -1 from the left side and the right side both equal the same thing, that means that the overall limit, where you don't write that left side, right hand side approach, is going to equal 4. Now, if you have a function that's rational, where you have an undefined element in your domain, like -1, and I'm just going to draw a little circle around that. Okay, I'm going to say, this is going to be a hole at -1 comma 4. And the reason for that is because limit as x approaches -1 is of f of x, sorry, equals 4. So if the limit exists, if there should be something there, even though it's excluded in the domain, that means that you just put a little hole in the graph. Like say, graph it like you normally would, and then you just have to acknowledge the fact that, hey, I'm not allowed to plug in -1. On our calculator, because there's millions of points technically around there, that 1 point won't even show up. You can't really, do that, but we could exaggerate that when we're graphing it and put a hole there. All right, so that's basically that. So now there's another domain restriction at x equals 1, right? So I'm going to just take what we have here so far. I'm going to just shrink that down, make that a little tiny and move it to the side. Now, in preparation for this, I also did another set of limits. X cannot equal 1. Why not? Like, why am I not allowed to plug in 1? We know that it makes the denominator equal 0 in the original, but we also know that in the simplified version of this function, if you were to look over here, if I cannot plug in 1 still, it's undefined, very much so. So when I say simplified version of this function, this is the most efficient version of this function, and you can tell by the red version of this graph, if I go to the actual graph of it, you see that at +1, you still have this break in the graph. It's they're not touching, so there's definitely discontinuity there. All right. So we want to know then, all right, well, even though we know clearly there's discontinuity, and we pretty much know there's a vertical asymptote there, right? But we want to know why not? Like, what's happening there? I'm being told I'm not allowed to plug in 1, so be really curious and be really bratty and say, fine, I'm just going to plug in values that are really close. So I'd go second table set. I'm going to change my table to 1 now. Still going to count by 0.01. And then I'm going to go second table again. Let's arrow up so we can set up what you'd call a neighborhood around 1 and take a look at the behavior of this function. All right, now again, in preparation for this, let's go back to the iPad so I can write on this. I want to know the limit as x is approaching 1 from just both sides. So I actually have to break this limit down into a left side approach and a right side approach, as you see here. If I get the same thing on both sides, then you would say the limit exists. Otherwise, there's no limit. So let's scroll down here. So there's our graph, and then here's our approach to 1. So let's look at the left approach. The left approach is on this side. So we have 0.95, 0.96, 0.97, 0.98, right? If you look up close here, here's 1, and then 0.96, 0.97, 0.98, 0.99. You see those little tiny values? I mean, I don't know if you can see them there. And what's happening as x is getting closer and closer to 1 on our graph. So this is the left side approach, and then I'm going to come in from the right side over here. Okay, so when you look at the table, as x is approaching +1 from the left side, I'm putting a circle around that just for effect. You don't normally do that. Here, put a nice little shaded circle. So as x is approaching 1 from the left side, we're getting 43, 53, 69.667, 103, 203. That hardly seems like it's leveling off. It's actually seems like it's growing without bound, right? Notice in both unsimplified and simplified, we still have an error, right? Error. And the reason is it remains undefined in both versions. So now if we do the right-hand approach, as x approaches -1 from the right side, okay, that means that we're coming in from the right here, and I demonstrated that over here on the graph. X is, when it's at 1.05, we're at -37, and then we're at -47 for 0.04, 1.03, -64 essentially, and then -97, and then -197. Okay, and we're only counting by 0.01, right? I mean, we can get closer than that if we want. But it seems to be getting really, really big and really, really negative at the same time. It's just getting deeper and deeper into the hole. And you can see that happening over here, right? So what that means is we technically have at that spot what's called a vertical asymptote. Put that right there. So that means as x is approaching, since I'm not allowed to plug in positive 1, as x is approaching from the right side, you can see that y, it's getting really, really, really negative, and it's going to go towards negative infinity. So the limit as x approaches 1 from the right side, for example, is going to be negative infinity. You can see that there. And the limit as x approaches 1 from the left side, right, of our function f of x is going to equal positive infinity. So if you have a limit that's equal to any variety of infinity, any variety. So in this case, you have on the left side we had positive infinity, on the right side we had negative infinity. If you have a limit that approaches any type of infinity, that's a definition of a vertical asymptote. And that's something that we can get at later. But so you'd say a limit as x approaches any constant of a function f of x equals some variety of infinity. Like, let's just say equals infinity. You know, I'll just say absolute value of this. So that way you just know it's going to equal some variety of infinity. That means that we have a vertical asymptote at x equals c, right? Or in our case over here, right, that means we have vertical asymptote at x equals 1. So the definition of a vertical asymptote is as x gets really close to the undefined value, y is increasing or decreasing with no bound. It's just getting really, really, really big. It's like infinity or negative infinity, which is technically undefined, right? You're not allowed to divide by 0. Well, there is no boundary to infinity. It's undefined, so it goes on forever and ever. Okay, so so how do you say the original limit then? What's the limit as x approaches 1? If it's different on both sides like that, positive infinity, negative infinity, what you would say is limit does not exist. There's no limit. Okay. Cool. So again, this definitely would require further explanation. This is a really long video, and I do apologize for that, and hopefully you'll get something out of it. But just in summary, when you're taking a limit of a constant, and the reason you would do that typically is because it's not defined, and you want to know what's going on there. If you take a limit at a constant, and you're getting a constant result on both sides. So if I take a limit as x approaches negative 1 from left and right, I'm getting 4 on both sides. That means the limit exists, and the answer is 4. If the limit exists, but it's not in the domain, that means you have a hole. Okay? Now, but if over here, you have x can't be 1, right? So this is going to be a vertical asymptote. The reason for that is the limit as x approaches, it's a weird arrow, 1 of f of x is equal to infinity. Again, I could say absolute value. Here, let me get rid of that little arrow that I drew here. From, like, we'll limit from both sides equals infinity of some sort. Okay, so if you have the limit from both sides of the undefined value is so y is approaching really, really big values from both sides of the undefined x value, that means you have a vertical asymptote, and that's what that means. The graph looks vertical from a distance. It just goes up, but the only value that's excluded is 1 and -1 in this case, but 1 yields a vertical asymptote, -1 yields a hole. And the last thing that we need to discuss, and we did this here, by the way, use limits to describe the behavior around each undefined value. Okay, so we figured out what's going on in the domain, right? We got that all sorted out. Now we want to use limits to define the end behavior. Now, the end behavior you learned about in polynomials, you know, it's like as x approaches infinity, y approaches infinity or negative infinity, whatever it is, right? So when you discuss end behavior, it's always a limit as x approaches infinity. So it's kind of like flipping it now. So we're going to say, what's a limit? And this is it's consistent. It's the same every time. As x approaches infinity of our function f of x. Okay, so, and then we want to know what's the limit as x approaches negative infinity of our function f of x. So you'd call this right end behavior. And I'm sure you would guess that this side is the left end behavior. Okay, so with a rational function, if as x approaches infinity or negative infinity, if y is equal to a constant, then what we have is what you'd call a horizontal asymptote. Now, horizontal asymptotes are not like vertical asymptotes. They're not excluded from the range necessarily or the domain or whatever. It's just what the graph looks like. It looks like a horizontal line on its ends. So if you look here at either of these, you can see that the graph does seem to be flattening out. So let's actually go over to the calculator again and take a look at the actual graph. So if you look at the graph, this is only from -10 to +10. Let's change our window to look from, let's go from -50 to +50. And see what's happening there. So you can see that the graph from this distance, just panning out like this, really shows you how the graph seems to flatline. So again, as x is approaching infinity, right? Like we've only made it up to 50. As x is approaching infinity, we're talking about really, really big numbers. So a great place to look at that again is just look at the graph. I mean, at the at the table. So if we look at the table and we say, let's start our table at 100. No, actually, let's start at 10. That's fine. Let's start at 10, but we're going to count by, I don't know, 20, right? So we'll go second table. Oh, it's nice that they're showing us fractions like that. Thank you. So that's quite unusual. Yeah, there must be something in the settings. I'm not going to edit this out just because I don't want to. So yeah, so let's go over here. Actually, I'm going to go. Let's go second. I'm going to show you something else that's sort of fun. Quit. We'll go to this main screen here. I don't know if you're familiar with the vars. I believe that if I go alpha calc, yeah, press alpha and then trace here. I'm curious about what's happening to our function y1, right? So I can actually evaluate the graph of y1 here. So I'm going to say, okay, cool, pick that of, so if I plug in like 10, for example, it's going to tell me 25/9. Wow, this is really interesting that it's doing this for us. There's a workaround for this. If I were to go up to here and say 10.0, it'll give me the decimal, right? So let's plug in let's take this same thing. You can just arrow up and hit enter again. I'm going to change this to 1000.0, and that's hardly infinity, and you're getting that number. And then I'm going to go back up again. Let's look at y1 and say, all right, let's go add a couple more zeros. And then say 0.0 because the calculator is just forcing rational numbers, exact numbers. So anyway, 2.999. All right, let's just be really, really bratty and see if we can force it to say 3, because it looks like that's where it's headed, right? 0, 0, 0, 0, 0, 0, 0. Okay, I don't even know what number that is, but all right, it just gives up and tells us 3. Now, if you were to take that and do the same thing on the other end, so right now we just did the limit to infinity. We just plugged in a really, really big number. Notice how they just kept approaching 2.77, 2.99, 2.9999. Y, as x is getting bigger and bigger and bigger, y doesn't seem to be doing much. It's just flattening out. So if I were to take this and throw a negative in front of it, right? Just go over here and I'm just going to insert, second, insert, and just toss a negative right out in front of that number. Notice how it's still 3. For that massive, massive negative number, I still have a 3. So if you look back at our limit, if you think about the function, what I just showed you there, the limit as x approaches infinity is going to be 3. And the limit as x approaches negative infinity is going to be 3. So this right here is an example of the definition, this like definition of a horizontal asymptote. So that means that if as x approaches infinity and or negative infinity, either way, with rational functions, if it's approaching infinity and you get a constant on one side, it will be the same thing on the other side with rational functions. So yeah, as x approaches both positive and negative infinity, the right end and left end behavior of this function is 3, right? So and you can look at the graph over here. If I go and draw a horizontal line now, that's not a horizontal line. Let's try that again. Okay. I'll place that at 3. You can see that the function actually wants to be like y equals 3. It's just flattening out. And from a distance, if you pan way, way, way out, you'll see that it looks just like y equals 3. So that's the end behavior. The end behavior is the line y equals 3. So that's basically what's happening there. And that's, that's something worth exploring further just by looking at other examples and stuff. But so yeah, the end behavior of this function is y equals 3. So you could say horizontal asymptote. So horizontal asymptote at y equals 3. And you actually write the equation of that horizontal asymptote too. So that's pretty much it for that explanation. I know this is super long. You could do this a lot faster, and you do once you understand what's going on. But this was the more in-depth explanation that sort of brought some limits into the situation and also gave you sort of hopefully a better understanding for what people are talking about when they use limits to explore the undefined, right? So if you look again at the title of the slide, exploring the undefined means literally I'm not allowed to plug in -1 and 1 because they're undefined in that original function, right? But also, if you look down here, we're using limits to describe the end behavior, limits to infinity. Infinity inherently is not defined either. So we truly are exploring the undefined with these limits for this particular function. And rational functions out of all of the functions are perfect for these types of explorations. All right, so hopefully that was helpful, and stay tuned for more postings.